about flight software randomization with a tool that we have developed that was proposed for my PhD. It's called toolchain agnostic software randomization, and we are going to see shortly what it's about. I'm going to introduce the concept of software randomization. Then I will also introduce measurement-based probabilistic timing analysis. We will see our tool and how it works, and we'll present some results about software randomization on Leon 3. Software randomization is a simple process in which we randomly change the memory layout of software without changing its functionality. You may wonder, why do we need to do that? So there are multiple reasons. The main one, which I'm going to focus for the rest of the presentation, is that this gives us in our software some nice properties which are useful for the computation of worst case execution time using probabilistic timing analysis methods. Another reason could be in order to isolate the effect of jitter when we perform performance evaluation. And another one that it's increasingly emerging now in space, as we have seen in some of the previous presentation, it's about security. So nowadays, a lot of security attacks exploit information about the timing or the specific memory layout of a program. So by changing the memory layout or the timing, we can defend ourselves from these attacks. Flight software workshop flight software usually has real-time properties. This means that it's not only enough that it works correctly, but it has to complete its functionality before a given deadline. And missing the lines can have catastrophic effects. Back in the day, we almost lost Mars Pathfinder because of a timing issue. And for this reason, we need to compute worst case execution time. On Monday, there was a talk from Marek. He explained that one of the most challenging parts when moving to RING 653 operating systems was to compute worst case execution time. And this becomes even more complex when we increase the complexity of the flight hardware we are using. For example, when we use deep memory hierarchies or multi-cores, this becomes very complex. One solution to this is through measurement-based probabilistic timing analysis. This is a relatively new method that can provide competitive results compared to traditional worst-case execution time methods. Unlike traditional method doesn't provide a single value for worst-case execution time, but as you can see here, it can provide a distribution, a probability distribution that can associate worst-case execution times with probabilities for this to be exceeded. And this can reach arbitrary low values, for example, less than 10 to the minus 16. This works by processing measurements using well-established statistical methods, such as extreme value theory. And because it's very simple in nature, it's quite industry friendly. And by applying this method, we can ensure that the execution conditions that apply at the moment that we perform our testing, our measurements, this will be the same or even be upper bound at the operation time. So let me give you a high-level idea of how this works. We know that execution time is not constant, usually follows a distribution. And when we are testing our software, we are taking measurements from the central part of this almost normal distribution. Then by processing this data with extreme value theory, we can predict the maximum of this probabilistic distribution, and we can reason about its worst case execution time. However, there is a catch. This only works if our software and hardware platform complies with some properties, what we call MBPTA compliant platforms. What does this mean? Simply that the execution times that we measure from our software, from end-to-end runs, need to be modeled by independent and identically distributed random variables. Independence means that the same program, when it's executed, it should not affect the execution time of another instance of the same program. Identical distribution means that also I'm observing the same probability distribution, so I'm executing actually the same software. In order to achieve this, we have to study which are the events that affect the execution time and make them either random or jitterless. And this way we can ensure that what we observe at analysis time, it will be holding at the operation time of the system. We can achieve this through time randomization. So we select the low-level sources of jitter, for example, the memory layout of our program, and we can randomize it while we keep our functionality unchanged. And this way we can capture the effect with a probabilistic law. The main benefit of this method is that we can now manage the complexity of complex hardware and complex software. We can apply time randomization in different ways, either at hardware or at software level. I have explored both in my PhD thesis. But in this talk, we are going to focus on software solutions, and in particular, the static software randomization variant. The idea of static software randomization is that before the program execution, we create a different binary with a random binary layout. And when we load this binary in memory, it will have a different memory layout. And because of the mapping of the memory to the cache subsystem, this will change also the mapping of the cache, the conflicts that we are going to get inside the cache, and this will be translated to different execution times per execution. Now let me introduce TASA, which, as I said, stands for Toolchain Agnostic Software Randomization. And the entire tool is based on a very simple observation that compilers generate program entities in the same order that it encounters them inside the source file. So if I change the location of my definitions inside the source file, this will be translated to a different memory layout. Before going to the details, let me introduce you to the ELF binary format, which is one of the most used binary formats. And it contains different sections. We have text, which holds the data, read-only data, as the name says, data that are initialized and never changed. The data section, which contains initialized variables, and the BSS that contains uninitialized variables or variables initialized to 0. And BSS is ensured that at program start time, all this area will be written to 0. And each entry of variables or elements that we have in the software, it needs to be aligned to their size. So now let's see how we perform code randomization. As I said, it's very simple. We just change the order of functions in our source code. This means that in C code, we have also to introduce prototypes. And in order to explore more memory layouts, we also add a random number of NOP operations after the return point of our function. So this, we can ensure that they are never executed. And this creates different order in the binary, as you can see on the right. And also the padding changes the size of its function. And this can also change the size of the entire segment. So this can have a cascade effect in the following segments as well. A similar idea is followed also in the randomization of the stack frame. The size of the stack frame depends on the number of variables and their types that we have in local scope. And also compiler introduces additional padding in order to make sure that addresses of its variable are multiples of their size. So this plays also a role on the exact size of the stack frame. In TASA, we propose two different solutions. One that we call interstack randomization, and artificially changes the size of the stack frame by a random amount. And this helps to randomize conflicts in the data cache among different stack frames. And we have also an intra-stack randomization solution that is simply achieved by reordering local variables and randomizes conflicts between the stack frame of the same function. So here you can see a visual representation of the application of this method. We introduce a randomly sized non-used array in order to achieve the inter-stack randomization. And we have also the reordering of local variables in order to achieve the intra-stack randomization. And then you can see on the right, by changing also the order, if we have variables of different size, this can change also the size of the stack frame because the compiler will introduce some additional padding as required. Exactly the same idea can be applied in the global data. The only difference in that case is that we have to be careful because different global variables go to different sections. As we said, we have read-only data, data, and BSS. So the way that TASA works is that first groups all the global variables that they go to the same segment together, and then we perform their shuffling. We have implemented TASA inside the Silk source-to-source compiler from Berkeley. It supports any C contract, including GCC extension. So this works with arbitrary complex C code, even with Linux kernel, and it's available as open source. So we take C code, we pass it from the preprocessor, and then we use a SIL functionality, which is called source code linking. So effectively, we create just a huge C file that contains all the source code of our application. Then we randomize it with TASA, and then you can use your favorite compiler to generate the image. So this makes our approach completely portable across any compiler and any architecture. So let me now talk a bit about the randomization of flight software. So in collaboration with Airbus, we performed a demonstration of this idea on a realistic setup. So they provided a mixed criticality software for an optical instrument based on deformable mirrors. And the application is executed on a hypervisor, Cisco Pike OS native. Here you can see a high-level description of the flight software. Mainly, we have two tasks. One control task, which is high criticality, and this is in charge of controlling the mirror displacement. And it's the one that interfaces with the spacecraft systems and has a period of 1 second. And this is the specific task that requires timing analysis. We have also an image processing task, which has lower criticality and computes the passive mirror deformation. And this task it's more CPU and memory intensive, and it's executed every 100 milliseconds. Both tasks are implemented in separate partitions on top of Pike OS in order to achieve time and space isolation. Some more information about the control task. The input is a 12 by 12 array of lenses, and each array contains 34 by 34 pixels. But not every lens is processed. In fact, only the ones that are most illuminated, which are more or less 70% of the lenses. This makes the application to have an execution time that depends on input data and makes it also challenging for the timing analysis. The hardware that we have used in order to execute this software was a custom implementation from Geisler, which resembles closely the GR740. It consists of 4 cores, Leon 3, separate instruction and data caches, and features also an L2 cache, which is partitioned. So each core can get one way of the cache in order not to affect the timing of the other one. This is implemented on an Altera FPGA with 100 megahertz clock. And this platform is available from Geisler from licensing It's called the Leon 3 probabilistic platform. It can achieve it comes with a configurable setting. It can have the hardware software randomization, or it can be used as a conventional deterministic platform, which was the case in this study. Because in that case, we have provided the the randomization at software level. So here you can see some results about the observed execution time of the control task. Something that is very interesting is that the software randomized version of the software was faster than the deterministic one. If we take here, you can see the minimum, the average, and the maximum observed time. You can see in all the cases, its bar it's a bit lower for the software randomized one, and the reason for this is if we take a look in the statistics from the CAS misses for instruction data and L2, it happens that the software randomized version provides a better layout, explores better layouts for the L2 compared to the pathological one that was the default generated by the compiler, and this makes the application going about 1% faster. Here you can see the results of the worst case execution time estimation. We can see a zoom of the previous figure. Here you can see two curves. With red, we have the observed execution times that we have collected, around 1,000 measurements. And then we process these results with extreme value theory, and we can create an upper bound probabilistic distribution that you can see here with purple. What is very interesting is that the difference between the maximum observed execution time and the execution time with the worst case execution time with probability lower than 10 to the minus 13, it's just 2%. Just to give you a perspective, uh, on Monday, Marek mentioned that there are some engineering margins that are applied for in order to compute this worst case execution time. I don't know exactly what is the value used in JPL, but I can tell you from the avionics domain, at least in civil avionics in Airbus. Usually, they use PowerPC 750. They disable the L2 CAS because it's really unpredictable, and this costs a lot in average performance. And they use a 20% margin in order to account for the worst case. And here, with this method, we just get 2% margin, and we are able to use a second level CAS. A limitation that we have currently is that we are working with C code. So in 2 weeks, we kick off a new activity with the European Space Agency, in which we will implement TASA in the LLVM compiler framework. And this will enable us to apply software randomization not only to C code, but also to C++ and other parallel programming models that are based on C++, like OpenCL and SYCL. Also, just to give you an indication that this doesn't work only on Leon 3, but as I said, it's completely independent on hardware and the compiler that we are using. In the Metasat program, we have done some preliminary analysis. We have executed software on top of Noel 5 with our custom AI accelerator, which is programmed with custom AI, custom ISA instructions. And TASA is able to software randomize even this custom software. And in another project, which is called Up to Date, finished in December, we have also made a prototype with TASA working with GPU code, CUDA. So this is really portable and can be used in different platforms and different compilers. So to conclude my talk, we have seen that measurement-based probabilistic timing analysis can simplify the timing analysis of hardware, of complex hardware platforms. Static software randomization is at source code level. It's a viable, mature solution for the estimation of worst-case execution time of flight software. And our solution is completely portable among different compiler tool chains and different hardware platforms. I'd like to thank all our funding agencies in different European funded projects. I have included a couple of resources in case that you would like to take a look more, but actually feel free to meet with me and discuss anything about this work. And with that, thank you very much for your attention, and I will be happy to take questions.
So one question, TASA from me. TASA seems like it was designed for performance optimization and worst case timing analysis. Maybe I'm misunderstanding. Could it also be used for bug hunting as well to uncover hidden implicit assumptions in data layout? You might have buffer overruns or things like that.
Yeah, actually, that's a very interesting application of TASA. Actually, when I was playing with this during my PhD, I was working with some embedded benchmarks. Embassy, it's a well-known suite used for embedded systems. And it happened that they had some buffer overflows, actually. So my software randomized version was getting crashes depending on the memory layout that we're generating. So yeah, that could be also used to expose hidden bugs in the code.
And I presume you save all the different layouts so they're reproducible, right? You can.
Yeah, exactly.
Okay. All right. Let's go to in person. We'll go over here first and then here.
I just had a question. You were talking about, looks like you're looking at effects of cache misses and context switching changes and things that can slightly change. Did you look at like effects of changes, like if you're doing like edge detection on an image? I mean, the time it takes to process that is very dependent on the actual source image, or if you're sorting numbers, the numbers that you're sorting. Do you do similar things with the input arguments to try to figure out the effective time in that way?
Exactly. That's something, a very good question and very good observation. So yeah, you have to be very careful how you apply this method. So typically, if you have an algorithm that it's input dependent, I mean, it's a well-known problem in the worst case execution time that we have to find worst case inputs. So usually, at least again speaking on the avionics side, it's based on the engineer's knowledge about the software, and they have to provide the worst case input for that. But as we were saying before about fuzzing, that could be also a way to extend this method to be able to compute worst case execution time also depending on different inputs.
Okay, we have no more questions online, so we'll take in the room.
Yeah, so this method looks very good for very stable software execution, but often our real-time processing has events that occur that you have to account for in your worst case execution timing, especially for time partitioning. Like you have an event and that kicks in a fault handler and it does event logging and recording. In your stream, you have to be able to account for that worst case execution. This seems to account more for the jitter in memory layouts and operations more than it does for that systemic worst case execution time. And that's what normally gets us in trouble in our time partitioning.
I think you refer also to input based variability, right?
Typically, something will happen because of a change in an input, a monitor trips, and it causes an event logging that takes a bunch of time that you didn't have left because you're already at 80% of your execution window.
Right. Yeah. I mean, that's a well-known problem, and yeah, we have to find a solution. Actually, for the hardware, as I said, we have both hardware and software solutions for that. And one interesting approach of the hardware solution is that we have developed a method that is able to provide probabilistic worst case execution time, no matter of the input. Of course, it's quite pessimistic, but for example, if you take different branches, we have a way to make them equally expensive, and the same thing if you have loops. So we can take this into account, and with only a single input, we can provide a worst case execution time that will hold for any input. But as I said, this is going to be expensive, quite pessimistic, and also works only when we have the hardware randomization enabled. Still, we are looking on how we can apply the same methodology based on software randomization. But I don't have a solution right now.
Great talk. I noticed that you are, well, you told us that you were basically doing a text-based munging of the code. So you reorganize things at the layer before they get to the compiler, which makes it very language specific. And that's what you were talking about, the C++ extension. I'm wondering why you didn't look at doing it at the link layer, so that you're essentially language independent at that point. Was it just the granularity of the layout is what you were shooting for?
Yeah, actually very good observation. Thank you very much for this question. As I said, during my PhD, I developed 3 different versions of software randomization. So I had the first implementation I had was completely dynamic. So I was going and patching every location of new functions, but this has a lot of pointer redirections. It's not good for flying software. Then the second approach was exactly what you mentioned at statically, but at link level. So this way it can work, but I cannot have stack randomization. It only works for functions. So still we need to modify the compiler, which again creates some problems of qualifying again the compiler. And we ran out in one case, in one of these projects that we were working, we applied software randomization in 3 different platforms. This Leon, the PowerPC used in avionics, and then we had an automotive platform from Infineon, which unfortunately we didn't have access to the compiler. So I had to devise a work that worked no matter of what the compiler is, and that was TASA. But yeah, the same idea could be applied at link level, and we could get a subset of what I was showing.
Thank you.
Thank you.
There is. I'll make a comment about an online question that just came in afterwards.
I'm curious if you're familiar with the stabilizer compiler and runtime framework from UMass Amherst, and how you feel this compares to the strengths and capabilities of that versus this.
Absolutely. So the second reference I put here, it's exactly stabilizer. And we have collaborated with Charlie in one of the first implementation that was the dynamic software randomization that I mentioned earlier, that we had to go and
how would you
patch.
compare the appropriate use cases and insights to be gleaned from either one?
So mainly the differences are in overheads. The dynamic software randomization has this overhead because we have to go and patch different locations.
Stabilizer is doing that.
Exactly.
Okay.
So actually, we used stabilizer for the dynamic software randomization. I just modified the way that it worked because stabilizer does this lazily. So the first time that you execute a function, you go and patch the location. But this is not good for real-time software. So I had created an eager version that does the software randomization before you start executing. But for large flight software, this takes forever. If you reboot, you have a lot of overhead. And yeah.
Thank you.
Thank you.
So the last question may need to be answered in the Slack channel. It's from David Keck. It says, has there been any comparison to this randomization method and data-oriented design with the Wikipedia link to the data-oriented design article? So I'm not sure if you're familiar with that.
Yeah, unfortunately, I'm not aware of that, but I will definitely check it.
Okay. All right. Thank you, Leonidas.
Thank you.